Okay, guys, so this video is about an introduction towards the vector space. Vector space is basically a set of vectors which should follow a certain set of conditions. All the vectors which are part of the vector space should be closed under addition, which means that if you add two or more vectors, the answer you would get as a vector should also be part of that vector space. The second condition is that the vector space should also be closed under multiplication, which means that if you multiply a vector by some scalar multiple, then the answer you should get should also be part of the vector space. The third thing you need to identify is that a vector space should contain an origin. So among all the set of vectors which are part of the vector space, origin should also be part of that vector space. Um, what we actually do is that we define vector space with the help of a spanning set. A spanning set is a set which contains vectors which are called bases. And every vector of that vector space should be a linear combination of those bases vectors. So if A, B, and C are the vectors which are called bases, then any linear combination of scalar multiples alpha A plus beta B plus gamma C could be part of that vector space. The other thing you need to identify is that the bases, which are A, B, and C, are supposed to be linearly independent vectors. Linearly independent vectors mathematically are such vectors so that alpha A plus beta B plus gamma C should not be equal to 0. So if alpha A plus beta B plus gamma C is equal to 0, so that means these vectors are linearly dependent, which means that from the linear combination of two vectors, you can get the third vector. So if they are not linearly dependent, and hence they are linearly independent, then the linear combination of two vectors must not give you the third vector. If linear combination of two vectors can give you the third vector, then this third vector is a redundant vector to be part of the bases. Because bases would have their linear combinations to give you all possible vectors of the vector space. So if third vector can already be obtained by the linear combination of two vectors, then I don't need the third vector as part of my bases. So it is not necessary for three vectors. But even if there are two vectors where alpha A is equal to beta B, then they are called linearly dependent vectors. That means a linear combination of A could give you a vector B. So if there are such linearly dependent vectors, they can't form bases. Likewise, for three vectors, alpha A plus beta B must not be equal to gamma C. If alpha A plus beta B is equal to gamma C, so that means a linear combination of A and B can help me achieve vector C, and hence that would inform the set of bases. The same thing applies to four vectors. So any such set of vectors whose linear combination can be summed up to give 0 with not all scalar multiple to be equal to 0, then such set of vectors are called linearly dependent vectors. And these linearly dependent vectors cannot form the bases. So bases can only be formed if these are linearly independent vectors. For example, if I would say that I have a spanning set which contains one vector as 1, 1, 2 and another vector as 3, 1, 4, then 1, 1, 2 and 3, 1, 4 are called the bases of that particular vector space. And the number of vectors you have in the spanning set is called the dimension. So the number of linearly independent vectors would be the dimension of that particular vector space or a subspace, and the set which contains the bases is called the spanning set. And hence, any vector which is part of the vector space should be a linear combination of scalar multiple of the two basis vectors over here. So it'll be alpha times 1, 1, 2 plus beta times 3, 1, 4. Which means, I can take some certain random values of alpha and beta and get myself the vectors which are part of the vector space or the subspace. Like for instance, if I take value of alpha as 1 and the value beta as 2 and plug in it over here, I get myself 7, 3, and 10. 7, 3, and 10 is what? It's a vector which is part of the subspace. Likewise, if I take a value of alpha equals -1 and beta equals 3, then that would give me another vector which would also be part of the vector space. A spanning set defined in this particular way should always follow the three conditions of it to be a vector space. It should be closed under addition. So if you have two vectors x and y, and if you add them up, then you know that you can form this vector with a linear combination of the value of alpha as 1 minus 1, which is 0, and the value of beta as 2 plus 3, which is equal to 5. So that means any particular vector, which is the sum of two vectors, can be obtained by a linear combination of the original basis vectors. Likewise, if you have any particular vector and you multiply it by a subscalar, so it should be closed under scalar multiplication as well. Like for instance, if I multiplied x by 2, so I know that I can get this vector 14, 6, and 20, that is multiplying by 2, can be obtained by putting in alpha as 2 and beta as 4. Likewise, if I take, since alpha and beta can be any real values, if I take alpha as 0 and if I take beta as 0, then that means that origin would also be part of this particular subspace. So it must be closed under addition, it must be closed under multiplication, and it must also contain the origin vector. So we could probably have a two-dimensional vector space, which contains all the vectors which are contained in the xy plane. So if you have a two-dimensional vector space, and you want to represent the entire of the vector space, then the standard bases could be 1, 0, and 0, 1. It's a two-dimensional vector space, and hence it should have two vectors as the basis vectors in the spanning set. So a standard basis would be 1, 0, 0, 1, which means you can get any vector with a linear combination of 1, 0, and 0, 1. For example, if you would want to make a vector 2, 1, then that means you will take alpha as 2 and beta as 1. So likewise, any two-dimensional vector can be formed with a linear combination of these two vectors. So this is a standard basis. Or you could take any two linearly independent vectors in a two-dimensional vector space. Two linearly dependent vectors must be parallel to each other. So here vector A and B are not parallel to each other. So alpha times A must not be beta times B, so they are linearly independent vectors. So any two linearly independent vectors must form a two-dimensional subspace. Since the original vector space is two-dimensional, so that means vector A and vector B should span the whole of two-dimensional vector space. So just like 1, 0, 0, 1 is an example of bases, likewise, any two linearly independent vectors in a two-dimensional vector space should form the basis. And you should be able to form all the vectors in that particular vector space with the help of these two bases. But they have to be non-parallel. So 1, 2, and 1, 4 can be used to form a basis, but 1, 2, and 2, 4 can't be used to form the basis because they are linearly dependent vectors. They are parallel vectors. So what I'm going to do in case if I have these two vectors to define a certain subspace, what I'm going to do is that I'm going to simplify this as 1 and 2 because I know that it's a one-dimensional subspace. And since it is a one-dimensional subspace, so it should only represent a line. So all vectors in the direction 1, 2 should be forming the subspace. Graphically, you can also identify that if I have A and B as the basis vectors. They can be the basis vectors because they're not linearly dependent. And since A and B are linearly independent, I can use them to form any vector. For instance, if you look at the vector C can be taken as a linear combination of B. So it will be 2 times B and minus half times A. That will give me the vector C. So I just like C, I can form any vector in two-dimensional vector space with the help of vector A and B. So they can also form the bases. So with two-dimensional vector space, you are only left with two possibilities. You have two linearly independent vectors, then that means it spans the entire of the two-dimensional vector space. Or if you have one vector, then that means that its dimension is one, and that represents a line passing through origin. But if you have two vectors which are parallel to each other, so they are linearly dependent vectors, and that means they do not represent the whole of the two-dimensional vector space, they only represent a one-dimensional line, and hence the dimension of that particular subspace should be one. You could also have three-dimensional vector space, and if you have a three-dimensional vector space, that means you're talking about a 3D space. So if you have a 3D space, that means that's a three-dimensional vector space. With a three-dimensional vector space, you again have either a possibility of spanning whole of three-dimensional vector space with the help of three linearly independent vectors. So either you can take a standard basis for three-dimensional vector space, which would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. Or any other three vectors which are linearly independent. If there are three vectors which are linearly independent, that means they span whole of three-dimensional vector space. A standard example of three linearly independent vectors is 1, 0, 0, 0, 1, 0, and 0, 0, 1. In case if you have two linearly independent vectors in a three-dimensional vector space, so that means these two vectors should represent a plane in a three-dimensional vector space. So linear combination of two vectors should give me all vectors which are lying in one particular plane. So if I have two linearly independent vectors in the bases, so that means the dimension is 2, and a two-dimensional subspace in a three-dimensional vector space should represent a plane. Whereas if I have only one vector in a three-dimensional vector space, so that means that represents a one-dimensional subspace, and hence it should be a line. So guys, we extrapolate the idea for the four-dimensional vector space. So when we have a four-dimensional vector space, again we can say that to represent the entire of the four-dimensional vector space, we can have standard bases as 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 1. So this forms the standard bases. Or you have any four linearly independent vectors such that alpha A plus beta B plus gamma C plus delta D is not equal to 0. So that means these four vectors in a four-dimensional vector space should form the bases. But if you have three linearly independent vectors, so that means that in a four-dimensional vector space, how do you know it's a four-dimensional vector space? It should have four components. So if in a 4D vector space, if you have three linearly independent vectors, so that represents a three-dimensional subspace. If you have two linearly independent vectors, so that means in a four-dimensional vector space, you have only a plane being represented by these two vectors. Or if you have only one vector, then it should represent a line. Okay, guys, so you have two different ways to find out the bases and the dimension of a vector space. If you have, let's say, a couple of vectors, maybe 2, 3, or 4, and you're not sure whether they are linearly dependent or independent, so you can apply a column space algorithm or a row space algorithm to determine yourself the bases vectors, and hence, since you would be able to identify the bases vector, you would be able to identify the dimension of that vector space as well. So using a column space, what you could do is that you can write down the vectors as the column of the matrix and then perform the steps of row reduction. Once you have performed the row reduction and written it down to a row echelon form, you would identify that the columns which contain the pivot variables would represent the basis vectors. But the original vector should be taken out for that. And hence the number of vectors would be equal to dimension. So, like for instance, if I have these four set of vectors, 1, 0, 2, 3, 1, 1, 4, 5, 1, 3, 7, 2, and 2, 1, 3, 4. And I want to figure out whether these four vectors are linearly independent or not. Hence, should they form the bases or not, I would input these vectors one by one as the column of the matrix. And then I will apply the steps of row reduction to simplify these. After getting the row echelon form, I'm going to be able to identify that each of the columns have pivot variables. You'd identify that there's a pivot variable in the first column, second column, third column, as well as fourth column. And hence, all four vectors are linearly independent. And hence, all of these four vectors would form the bases. But the basis vector should be the original vectors. So I can say all these four vectors should form the basis. But since I also know that we're talking about a four-dimensional vector space, and a four-dimensional vector space having a four-dimensional subspace means that represents entire of the four-dimensional vector space. So I could also write down the bases as 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 1. Now, for instance, let's say that you had done the row reduction, but you had gotten yourself the last number. Just suppose that you had gotten the last number as 0. If you'd gotten the last number as 0, so that means that only the first three columns contain the pivot variables. And since only first three columns contain the pivot variables, so that means you would only pick the first three vectors as your basis vectors. Or let's imagine that you had gotten yourself a 0, 0 in the second last row as well. So that means you would have been having pivot variable only in the first column and the second column. So that means only the first column and second column would have represented the bases. But in this particular case, that's not what's happening, and hence you have a four-dimensional vector space represented by these four vectors. Now, the second algorithm that you could do is that you can also perform a row space method to identify the bases and dimensions. When you do a row space, you input the vectors as the row of the matrix and then again perform the row reduction step. And all non-zero number of rows should be representing the bases. The good thing about this method is that you can directly take vectors from the reduced form. So like I have just chosen the same four vectors, but instead of putting them as columns, if you might notice, I put them as rows of the matrix. The first vector becomes the first row, the second vector becomes the second row, the third vector becomes the third row, and fourth vector becomes the fourth row. And then I perform these steps of row reduction, get a row echelon form. And once I get a row echelon form, you might notice that I have all four rows as non-zero rows, as was anticipated because I was using the same vectors with a different method. So I was expecting to get a four-dimensional vector space. So I know that in a four-dimensional vector space, if I have a four-dimensional subspace, so that means it should be representing the entire of the vector space. So either I could write down my, now the best thing about this method is that I can write the bases from the simplified form. So this is a row echelon form. I can also reduce it down to a reduced row echelon form and hence get myself more simplified bases. But whatever you get up after row reduction should form the bases. So here I can directly say that one of the bases vectors is 1, 0, 2, 3, the other one is 0, 1, 2, 2, the next one is 0, 0, minus 1, minus 7, and 0, 0, 17. But since I also do know that if it's a four-dimensional subspace and hence it spans the whole of V4, I could also have taken the bases as 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 1. So that's also something I could have done.